In this video we're going to examine how noise in one part of a circuit causes noise in another part. That process is called referring noise because the original noise doesn't go away, but it'll appear larger or smaller when you examine its effect at other locations. The first rule of moving noise around is that noise variances add, which means that noise voltages or currents would add in quadrature, not directly to one another. Like last video, we're not going to be diving too deep into the derivations of where these noise rules come from, but a quick demonstration of this principle is to imagine two resistors in series. Each resistor creates some voltage noise variance, and we can see that on the left. On the right, I've evaluated the voltage noise variance of their series combination, which is equal to the sum of each of their individual voltage noise variances. And that goes to show that voltage noise variances add. If the resistors were in parallel, you'd see the same behavior holds for current noise variances. So the big takeaway here is that variances add, so don't directly add noise voltages. You always have to square them first. The next important rule for moving noise around is that noise variance is scaled by the square magnitude of transfer functions. We're talking about noise variance here because we know noise variances add, so it's common to think about all the noise in the system in terms of variances, either voltage variances or power variances, depending on your taste. One weak justification for this transfer function rule is to look at the units of noise variance and the units of a transfer function. Noise voltage variance density has units of volts squared, while the transfer function has units of volts per volt. So you'd have to square the transfer function in order for dimensional analysis to work out when you apply it to a voltage variance. You can see this rule in action. Real proofs of that rely on fancy words like autocorrelations and power spectral densities, which you can learn about in a random processes class. You can see this rule in action on this slide. A voltage noise variance is fed into an amplifier that has a DC gain of A and a first order roll-off at high frequencies, and that's pretty common for amplifiers. We can see that the noise spectrum at the output of the amplifier is scaled by A squared at DC, and it rolls off at 40 dB per decade, which is twice as fast as the transfer function. So this indicates that the noise spectrum at the input of the amplifier has been multiplied by the transfer function of the amplifier squared. So in summary, noise variances add, so don't just add noise voltages or currents. And noise variance is referred from one part of a circuit to another by the transfer function squared.